Okay.
We're on.
All right. Good morning, everyone. Thank you for coming. It's a great pleasure to have here today Dr. Yue M from Harvard University. Dr. Liu was graduated from Shanghai Jiatong University, and got his PhD from University of Illinois at Urbana-Champaign, and where he actually got his PhD in electrical engineering and MS in mathematics in 2007. He was at the University of Illinois as an RA and worked for Microsoft in Asia, in Beijing, and Siemens Corporation in Princeton, New Jersey. Following that work, he went to PFL in Lausanne, where he was a postdoc, a research scientist at PFL in Switzerland. And in 2010, he joined Harvard University, the School of Engineering and Applied Sciences. He is a recipient of several awards, one of them being the Most Innovative Paper Award at the IEEE Conference, ICIP, IEEE Conference on Image Processing in 2006, and also another Student Paper Award in 2007. He was also presented an award at the Siam Seas Conference in 2007, and he's received several awards, and so I don't have time to go through all of them, but he's also he received the ECE Illinois Young Alumni Achievement Award in 2015. And it's a pleasure to have you here, and thank you for coming. The floor is yours.
Okay. Thank you very much, Professor Krim, for the very kind invitation and also introduction. It's my pleasure to be here. Can everyone hear me clearly? All right. So today I'm going to talk about some of recent work on analyzing randomized row action methods for high-dimensional estimation. I'm going to explain what row action methods are, but let me first acknowledge my students and collaborators, Ameya Gaska, who's my first PhD student. He graduated last summer, and he's currently at MIT Lincoln Lab, and Hong Hu and Chuang Wan, students in my group, and Gen Li, a visiting student from Tsinghua University. Okay? All right, so this line of work started when we were considering a very, very simple problem. Suppose you have a vector x that you want to estimate, and you observe this vector through a linear system. So the measurement y on the left-hand side can be obtained as a matrix, some sort of matrix A multiplied with x, potentially with additional noise, right? Okay, and you know the system matrix A. You observe y, and you want to reconstruct x. So as simple as it gets, right? So what you want to do is, suppose you use a least square. You are solving a minimization problem, where the cost function is a summation of quadratic terms, and each term is associated with one of the rows. All right. Now, since we have written out, the least square problem in this sum form, we might as well consider a more general problem. The general problem that we consider is that you want to minimize a function that can be written as a summation of a very large number of cost functions, f1 to f of m. Each function is associated with some parameter theta 1 to theta of m that can be deterministic or random. Okay? This is, in fact, a very general problem. If you choose these functions appropriately, you will realize that a lot of problems in signal processing, machine learning, like imaging, sparse recovery, adaptive filtering, are all special cases of this problem. And it's also very important because its applications are ubiquitous in many fields of science and engineering. So here I just mentioned a few examples, like from biomedical imaging to seismic imaging, from very large-scale data analysis to the monitoring of cyber-physical systems. Okay, so going back to our problem, for the linear least square, this problem has been literally studied for hundreds of years. We think we should have already known everything that is to be known about this problem, the solution structure. Even for the more general system with potential linearity and so on, this has been studied before. For example, in the statistics literature, this is sometimes referred to as the M estimator. Okay? But if you look at recent papers in the community, you'll find there are a lot of interest in revisiting these problems, even for the simple linear case. Okay? And to me, these new interests are driven by the challenges associated with modern data sets and also by the unique features of modern computational platforms. First of all, we are studying very large data sets. So both the dimension n and the number of equations m can be very large. In fact, they can be so large that the data have to be stored in a distributed fashion. So at any given time, we can only have access to a partial subset of these data. Or you can have access to a massively parallel computing platform with hundreds of thousands of cores, but each core can only handle a very small amount of memory with limited computational power. So in this case, the algorithm, again, has only access to a portion of data at a time. Or the data can be reviewed one by one in a streaming fashion, right? Now, there's also this classical challenge of directly solving a non-convex problem, because later part of the talk, I'm going to mention reasons that why we want to forget about convex relaxation, directly attack a problem in its original non-convex form. Okay? So in this line of work, we're going to consider some sort of iterative iterative method that I think are uniquely positioned to address some of these challenges. These methods are very, very efficient. Per iteration has a linear complexity. They can start reconstructing based on partial data sets and also on the fly without the need to wait for entire data to be revealed. And as I will show, randomness is a very important component of these class of methods. And there are several sources of randomness. One is by the nature of the problem. We might be studying an ensemble of problems. So in this case, theta 1 to theta m can be random, or they can be by design. We introduce artificial randomness in this algorithm to get performance guarantees, or it can come from the fact that we are implementing these algorithms on circuits or over communication networks, and the circuits can be noisy, and also communication links can be noisy. Okay, so these are also additional sources of randomness. Yes. Yes. You can, in the special case of linear, just say linear least square, the thetas are the rows of the matrix, but it can be very general. Yes, these are just parameters of these functions. Okay, all right. So the kind of questions that we study are the following. Of course, the classical question people ask when you have an algorithm is the convergence issue. If it converges, if so, converges to what? And also because you are studying the large system limit, there are typically phase transition behavior in the limit of n and n go to infinity. But in our work, we want to study something more refined. We want to study so-called the dynamics of this algorithm, meaning that we want to know the exact performance of this algorithm when it is still tending towards the convergence point. Okay? Because in many cases, especially in the large n setting, we cannot afford to run this algorithm to the very end. Okay? We have to stop at a certain point. All right? And there's this issue of algorithmic or dynamic phase transition versus static phase transition, which I'm going to just say, I think, talk about a little bit in the later part of the talk. All right? Okay. So here is an outline. We're going to first start with the simple linear case. That's a warm-up. And I will show that although it's a very simple setting, there are still quite a number of interesting questions, and there are even some very challenging open questions left in this setting. And then I'll move on to the more challenging nonlinear and non-convex system, and I will focus on the case of so-called phase retrieval, or solving a quadratic system of equations. And in both cases, the protagonist of this line of work is a class of randomized projection, iterative projection algorithm. Okay, so first, the linear case. Now, we consider linear case, and for simplicity, let's not even assume there's noise. It's a noiseless or consistent system equations. We're given y is equal to a times x, and we want to find x. Okay, and this is an x, and then we know that every given equation gives a linear constraint on the possible location of x that x can be. So every equation gives you a linear constraint, and we know the true x lives at the intersection of all these x. a very simple algorithm is that you start with any initial guess. It can be a random guess, and then you pick one constraint and you project. Okay, want to enforce that constraint, you pick another constraint and enforce, and after a while, you will go into converge to the true solution. Okay, that's a very, very simple algorithm. It's also a very old algorithm. It was first proposed by Kaczmarz in 1947, and depending on the community you are from, it is sometimes also known as the algebraic reconstruction technique. It's also a special case of projection onto a convex set. The algorithm is very simple. You start with any initial guess, and then you pick a constraint, and you sort of project or enforce that constraint. And then you move on to the next constraint, all right? And then you go down, you start from the first constraint, you go down the list until you reach the very end, and then you do it all over again, okay, in this in a cyclic fashion. Although it's very simple, it's a key algorithm behind the first CT scanner that won Hornsfield and Cormack the Nobel Prize in 1979, and also different variants of this algorithm are still being used today. So if you go through, or your baggage go through airport security scanner, chances are that some versions, some variants of this algorithm are still working behind the scene. All right. So this is a very simple algorithm. It's also pretty natural to convince yourself that you will have a convergence after a while. What is challenging about this scheme, or what is not nice, is that the speed of convergence is difficult to quantify, because the speed of convergence depends on the exact order at which you pick these constraints. So this is one order. It's pretty slow because you are cycling through all these constraints, but you can have a different order, which is much faster. But it's very difficult to know a priori what will be the optimal order, right, to pick these constraints. But practitioners know how to solve this problem, because you don't need to go through these constraints in a round-robin fashion, right? You can randomize. Okay, you just say every time I randomly pick one constraint and I project. Typically, the performance is much better than the worst case. Now, but it was so my student came up with this cartoon. So you have to have the correct row order, otherwise the performance, the speed of convergence is going to be bad. All right. So it was only recently that Thomas Stromer and Roman Vershinin, they analyzed rigorously the performance of this algorithm. They considered a particular scheme that at any step of the iteration, you pick a row, AI, with a probability proportional to the square norm of that row. Very, very simple. It's not a special choice. Actually, you look at their formula, the derivation, it can be any probability distribution, but just have a more complicated formula. Now, and what they say is that the MSC, the mean squared error of this algorithm, at any iteration, so n is the number of iteration, has exponential decay. And I want to just emphasize that the expectation here is taken over all the random choices the algorithm could have taken, right? Because it's a randomized algorithm. And they show that the MSC has exponential decay, and the decay rate, the bound of this decay depends on the condition number. Okay, so essentially, the more well-conditioned, the better conditioned this matrix is, the faster the decay. Okay, this is the first work, but after that first work, there are a flurry of follow-up work. A lot of interest in the literature, in the community, about studying more generalized version of this algorithm. For example, you can study the noisy case, almost sure convergence instead of mean square convergence, finding the least square solution instead of finding a consistent solution, and also there is some generalization in terms of a randomized iterative sketching. Okay, so I don't need to go through all the details, but there are all variations on a common theme. And the common, the game in this field is that you study a sort of algorithm, and you want to show that this algorithm will have exponential convergence. Okay, you prove a bound. Okay, the MSC goes to 0 or goes towards some error floor according to a speed that is bounded by a term. Okay. Now, what I want to show next is that for all these very general class of algorithms, there's a very simple formula, a way of computing the exact MSC instead of having a bound. Okay, and first of all, let's look at why this type of algorithm should converge. Okay, or the MSC should have exponential convergence. Now, what I show on the top is the evolution of this algorithm, right? So from the previous iteration, which is a vector x of k minus 1, you go to x of k with some update. Okay, Now, and then because we care only about the error, so let's subtract from both sides the underlying true signal that we want to recover, and then we call this difference zk. Is that manipulation doesn't really matter. What matters is that we know from the previous error vector to the new error vector is nothing but a matrix multiplication, and this matrix is an orthogonal projection matrix onto the constraint. It's very, very simple. And now if you do k steps, then what you are getting is a product of these k projection matrices multiplied with initial error vector. The only thing that is interesting is that these matrices are random, because at every iteration, you're going to randomly pick one of these many possible projection matrices. Okay? Now, it's also easy to show that, to see that why this algorithm should converge, because each matrix is a orthogonal projection matrix, so the largest eigenvalue is bounded by 1. So it's non-expansive, right? And things are never going to blow up. Now, the only thing that is not so nice is the largest eigenvalue of these matrices is actually equal to 1, because it's an orthogonal projection. There are invariant subspaces. Okay, so that means these are not strict constructions. Yes.
So when the types of results that you're giving us about the mean square error,
yes,
I'm assuming that there are some assumptions being made on the matrix or the signal, or what's being assumed here?
The matrix is arbitrary. Of course, say we show that this will converge to 0, then assumption is that this matrix has 4-column rank. If you don't have 4-column rank, there will be an invariant subspace you cannot touch. But if you modulo that subspace, it still has exponential decay. Yes.
So the expectation is only with respect to the derivative.
Yeah, there's nothing random about the matrix. This is not spin glass yet.
And
Yes.
nothing random about the signal either.
No, the signal is arbitrary. This is,
okay,
yes.
Noise in this case. Got it.
Yes, noise in this case. If you have noise, then there is an error floor. Yes. But the exploitation does not need to take over the noise. The noise is like, this is like a numerical linear algebra. The noise is arbitrary perturbation. Yes. All right. So, as I said, the thing that is a little bit worrisome is that these are not strict constructions, because the largest eigenvalues is actually equal to 1. But what is nice is because these are randomized. Okay, every time you have a random matrix, so on average, it's a construction. So this is just average construction property. So that's the reason why we should morally believe that this algorithm will have exponential convergence. Okay. So here, I think end of 2004, we had this result. A formula essentially computing the exact MSE of this very large class of algorithm. And it's not only about Kachmars, it's also other algorithms like iterative projection and sketching and so on. They follow this common and very simple structure. We're saying that the MSE of this algorithm at any iteration n is equal to a product of 3 terms. So if you can see, on the right-hand side, you have 3 terms. You have 2 terms on both sides. The rightmost term depends on the initial error. Okay, so the larger the initial error, the larger the MSE, and the term in the middle is a matrix raised to the power of number of iterations. Okay, and this matrix can be shown to have a largest eigenvalue strictly smaller than 1, so it is going to be driving this MSE down to 0 exponentially fast, right? Okay, and it's raised to the power of n, so the more iterations you have, the lower the MSE. Before I talk about the idea behind how you get this formula, let's just first look at some numerical simulations. Because these are randomized algorithms, so what we show here, the gray faint lines are different realizations of this algorithm, because randomized, so you can have a little bit fluctuation. And the blue line is the empirical average of MSE, and the green dashed line is what the formula is predicting, so it's a verification this is correct. And also we show on the same figure the best bounds in the literature. Okay, so there are some bounds. Clearly, we can see that the bounds are overstating, are being a little bit pessimistic, because the vertical axis is showing log scale. Okay, now on the right, it's the same experiment but with a different matrix. So this matrix is a CT matrix. It's a real matrix people use in in CT reconstruction. And for this particular case, the bound is even worse, right? There are several orders of magnitude too loose. Okay. Now, for people working on theory, it's also always nice to be able to get this exact MSE. But for practitioners, it's also important. Imagine that you are a user of this algorithm, and you want to make sure that my MSE is below 0.1. Okay, that's your requirement. If you only know about the bound, if you look at 0.1, you would have to run this 1,000 iterations. But if you know the MSE, then maybe 100 iterations is enough. You know that's you can guarantee that level of a performance. And in practice, having fewer number of iterations means that you want to ask patients to spend less time in a scanner. You have faster reconstruction and so on. So which is a pretty important consideration. All right. Okay. So here is a proof. Okay. So this is the original proof, and then we use some identities. And I'm not going to go through this because this is our first how we originally got this formula. But later, after writing our first paper, we realized that there is a much simpler derivation to just approach towards that formula. So here is the idea. The idea is the following. As I said, zk is the error vector at end of every given iteration, and from the previous error vector to the new error vector, you multiply it with a random projection matrix, Q, random matrix, right? Okay. Now, if we want to take the expectation of this error vector, it's simple because first of all, this which matrix that I choose is independent of my current error vector. I independently choose one. So Q and zk minus 1 are independent. And also, because it's matrix vector multiplication, it's linear. So they factorize. That means expectation of zk is equal to expectation of matrix times the expectation of the previous error vector. And then if you iterate, this is nothing but raising the expectation of the q to the power of k. It's very simple. Okay. But we don't care about expectation of error vector. We care about the MSE, which is the expectation of the squared norm, okay, which is nonlinear. So we cannot directly apply the trick above because you have to use linearity to factorize this expectation. Now, the simple trick that we use is the following. We know that the MSE is nothing but a row vector times its column, right, column version. But we can rewrite it as a trace of a column vector times its row. Okay? That's equivalent. Now, instead of keeping track of the vector, we keep track of this rank 1 matrix. And then you can see that the dynamics of this rank 1 matrix, the error vector and its transpose, it's a rank 1 matrix, is related to the previous rank 1 matrix in this way. It's sandwiched by two random qk. Now, in fact, this is still a linear operation. To convince yourself, you can say I write the vectorized version of this matrix. And then you can say the vectorized version of the matrix is equal to this q and canonical q times the vectorized version of the original matrix. So it's a linear operation. So we can apply exactly the same trick as we mentioned on the first line. Okay, so it's a random linear recursion, and then you can take expectation over this canonical matrix and raise to the power of k. That's really the very simple idea behind this derivation. Okay, all right. Okay, so as we said that according to our formula, we know that the MSE will have exponential decay. Okay, so after running this algorithm for a while, the speed depends on the exponent of this exponential decay, which we define as a gamma of a. Okay, that's a limit of 1 of n number of iterations log of the MSE. Okay, that's the error exponent. And this error exponent can be computed because the reason that MSE is going to 0 is we are raising a matrix to the power of n. So the speed of decay is really governed by the largest eigenvalue of this matrix. Okay? And here in the formula, there are parameters pi. The pi's are the probabilities at which we choose each row. Okay? So we can leave these as free parameters. Then there is this obvious question of optimization. Suppose I want to have faster decay. What is the probability distribution pi that I have to choose to minimize the largest eigenvalue? And this is a convex problem, so we can solve it using semi-definite programming. Now here, this is just a very simple demonstration. here we consider a matrix with 3 columns. So every row is a point in 3-dimensional space, which can be represented by a point on the sphere, right? Okay. Now, and then these, just say these points pointing towards different orientations of these row vectors, and we run this optimization algorithm. We find the optimal sampling probability. We use color to represent probabilities. Darker means higher probability, lighter color means lower probability. And we can see that, intuitively speaking, this sampling probability makes sense, because there are regions here that are overly represented by these row vectors. They are very crowded, meaning there are a lot of these similar row vectors, so the assigned probabilities are low. But there are also regions here that are sparsely populated. Okay, so these are explorers, and then we assign higher probability. Okay, this is not done by hand. This is done just by solving this optimization problem, right? Of course, this is only intuitive explanation, but let's look at the actual performance. We can see that compared to the uniform scheme, the scheme studied by Stromer and Verschining, versus the optimal scheme, sampling, what you would change is the sampling probability. After 20 iterations, there are about 37 dB improvement, and the red line is the performance of a scheme that's also using optimization, but what they do is to optimize an upper bound instead of optimizing over an exact MSE, which is what we are doing here. And we can see that knowing the exact MSE also has some benefit. You can have still around 12 dB of improvement, right, by knowing the exact MSE, right? Okay. So and then here is something that was surprising. We didn't expect to see this behavior until we actually ran the simulations. I think it's also interesting, so I want to share this phenomenon with you. So we know that this is fundamentally a randomized algorithm. So every time you run it, you can get different results, right? Okay. So what we do is we run this algorithm 1,000 iterations. That's one trial, but we run it many, many trials. Okay. For each trial, we look at what the MSE we get. Okay, and then we plot it in a histogram. Okay. So there are very successful trials reaching MSE 10 to negative 24. That's very, very precise. But there are also less successful trials with MSE around 10 to the negative 16, right? Okay. So these are the histogram. And the red line is the empirical MSE, the average number, versus what we predict. Okay. It's a match. Again, it's a verification. And the green dashed line is the original bound. Clearly, the bound is very pessimistic, because here there are 8 orders of magnitude difference, right, in terms of what the bound is saying and what is actual performance. But clearly, there are more to the story, because you can see the MSE is not in the middle. The middle should be the bulk, the typical behavior of the performance, the typical performance of this algorithm. But the bound is still being a little bit pessimistic. Yes?
So is this maybe connected to, I mean, it has the appearance of a log Gaussian type of distribution.
Yes.
Obviously, the mean of that type of distribution is much, much larger than the median.
Yes. So that's the issue. So thanks, Dor. The issue here is that, you know, I think I'll come back to this issue. And another way to look at this phenomenon is that these gray lines are the sample path of this algorithm. The MSE clearly is not telling us the typical performance, which should be in the middle, right? Okay. So it is being a little bit pessimistic. Okay. What is the reason? The reason is that if we go back, look at the histogram. There are these very bad instances, okay? Because here, this is 10 to the negative 16 versus what is the average performance, which is 10 to the negative 20, right? That's 4 orders of magnitude worse than a typical performance. These are very, very bad realizations, but they are also very rare, because the probability is very, very small, right? Okay. But if you compute the MSE, you average over everything. Although the probability is small, but their contribution, once they happen, is very large. Okay, so the MSE is unduly influenced by these rare events, which we shouldn't really worry too much, right, about. So that's the reason. Okay, as this is exactly what Dor was saying. Now, how do we fix it? So to fix it, we have to redefine the error exponent. The previous error exponent is taking expectation and then take log. Then you are averaging over a random variable with exponentially wide dynamic range. This is going to create problems. What we say is you should take log and then take expectation so that you are normalized. You are averaging over some order 1 term. And this is, it doesn't, we use the jargon of crunched error exponent. It doesn't really matter. But the problem is, although this definition we think it makes sense, it's much, much harder to compute than before because log is a nonlinear function, and then you take expectation of log. Okay? For people studying dynamical systems, this is also known as the top Lyapunov exponent of a random dynamical system. There are even papers written about why this is very hard to compute, okay, in general. So what we did was to study this problem using a so-called replica method in a naive version. Okay. Now I don't think I want to go to the details, technical details of this method. Another way for engineers, another way to understand this is you can say that you can assume from this histogram you can see that on log scale this histogram is Gaussian. Okay. So the distribution we assume is a log normal distribution. If you know how log normal distribution, then the quantities that we compute can be obtained if you know the second and the fourth moment. Okay, and then there are formulas for computing the second and fourth moment. From the second and fourth moment, you can do a linear interpolation. You get your estimate. All right. So I'm not going to the details, but here this is I have to say this is not a proof. Okay, this is only some approximation, but in our test it works pretty well. So here the red line is what we get by using this so-called crunched error exponent. It predicts it's aligned better with the typical performance of this algorithm. All right. Okay. Okay. So I want to move on to the more general case because linear case is still simple. By the way, so what is the open problem? The open problem is actually computing this this quantity. This is a very challenging question. Okay.
So in a sense, sort of in English, that you're saying basically that in one case where you were assuming that
yes.
the error was Gaussian.
The error is log normal. Yes.
In the other case, it's actually the log of the error is Gaussian. And it's
yes.
More, and it's
yes.
more accurate that the log of the error be
yes.
Gaussian than
yes.
the other.
To rephrase this question, the error is approximately log normal. The log of the error is Gaussian. Because of this, it doesn't really make sense to consider the previous definition.
Right.
It makes more sense to consider the second definition. That's yes. Yes, you can say I captured the typical behavior instead of the real events.
Let me also mention, for the audience, a general comment that this type of behavior also appears in finance in a random walk, because we have a random variable which is multiplicative, so we're either going up by 1% or going down by 0.5% or whatever. But then they're because it's multiplicative, they're getting added up in a logarithmic way, which is exactly what we're seeing.
Yes. Yes. Okay. Thanks. All right. So let's move on to the nonlinear case. Okay. So this is the general problem setting that we have. Again, we want to estimate an unknown signal, which is an n-dimensional vector, and we have a collection of sensing vectors A of m, and we take the inner product between A, m, and x star, but we observe the inner product through a channel given by a conditional distribution py given inner product, right? And we observe y. In the linear case, the channel is identity, right? You just directly observe the inner product. But we consider the more general case, you have a channel with a conditional distribution. Now, this is very general because, for example, in image reconstruction, the inner product can be the total amount of light impinging upon a pixel. But what you observe, what you can measure on this pixel are photon counts. And the photon counts are Paulson random variables whose mean expectation is equal to this inner product, right? Okay, then in this case, P is a Poisson distribution, right? Now, and there are also other cases, but just for concreteness, we're going to focus on this problem so-called phase retrieval. So what is phase retrieval? It's very similar to the linear case, except for that after the inner product, we take absolute value. Okay, we are, in the real value case, missing the plus or minus 1 sign information. In the complex value case, we're missing the phase. Okay, now, if I tell you y1 to y of m, I want you to reconstruct x star that is equivalent to guessing the missing phase. So that's the reason why it is called phase retrieval. And this problem first arose in X-ray crystallography. It's a very important technique that was, again, behind this discovery of the double helix structure of DNA. Okay, it's a very important technical breakthrough to be able to infer the structure of these molecules, like DNA molecules. But there are also other instances in signal processing communications, such as blind deconvolution and so on, where these kind of problems also arise. All right. So, okay, I think first, what we want to do is to consider, just say, this general setup. Suppose we want to estimate x using so-called maximum a posteriori probability estimator, MAP estimator. We're essentially solving this minimization problem, which is a summation of these individual cost functions. That's very similar to what is a special case of the general framework we mentioned at the beginning of this talk, right? But what is the challenge? The challenge is that in many cases, these negative log likelihood functions are not convex. Okay, these are non-convex functions. So we don't know how to solve it directly. And what people do, a typical solution, or in fact, state-of-the-art approaches are to use convex relaxation. Okay, so you want to find a convex relaxation of this original problem. For example, in the case of phase retrieval, a way of convex relaxation is to go to the matrix domain and so on. So we don't need to worry about the details, but there's a problem of this convex relaxation scheme. The solution, although they are in principle solvable, you have to use so-called semi-definite programming to solve these convex relaxation problems. And the computational complexity is n to the power p, where p is greater than or equal to 3. And n is very large. Okay, so, but if you run standard semi-definite programming on your computer, maybe you can handle n equal to 200. Okay, that's about it, right? But for phase retrieval, n is supposed to be the number of pixels in an image. That can be millions, okay, tens of millions. So there's absolutely no way for this kind of a semi-definite programming approach or convex relaxation-based approach to work, despite the fact that you can prove beautiful theories about its performance and so on. But you can, once you try to actually implement these, you cannot do it. So that motivated us to consider the non-convex alternatives, meaning that we don't want to do any relaxation. We want to directly handle this original non-convex setting. All right. So let's focus on this concrete case. Why is it non-convex? Now, imagine you don't have these absolute values. Then that's exactly the same as the linear setting. Okay, you get the linear measurement, and then we know the true solution. The orange dot is at the intersection. But because we are missing the sign information for every subspace or constraint, for example, the red one, there is an ambiguity subspace, right? It can be plus or minus 1. And this is the same for the other subspaces. And you don't know which point to project to. That's the reason why you have non-convexity. So we can consider a very, very simple algorithm. It's just an example. The simple algorithm that we consider is the following. What you are missing is the sign information, the sign of this projection. We don't know it. But let's just say that we replace the actual sign information by the sign information obtained by the previous estimate. Okay, that's just a simple scheme, and you can also understand it as a Newton's method. Okay, and we want to analyze algorithms like this. Okay, and we want to also hopefully get performance guarantees, although this is a non-convex problems. Now, here is just a little bit specifics of the settings that we analyze this problem. First, we assume that the measurement vectors are coming from an ensemble, for example, Gaussian ensemble, and the dimension n of the signal and the number of equations m are very large, and they grow to infinity at proportionally. Okay. Now, we want to study the map estimator of this problem. So this is the optimization problem, and what we do is at any given iteration, we pick only one of these functions. And for example, you can run a gradient descent, a proximal step, or a Newton step, is addressing only one. And then for the next iteration, you go to the next one, right? Okay, that's a very, very simple algorithm. Now, this is the generic form of this iteration. And as a specific requirement, we consider so-called one-pass algorithm or online algorithm, meaning that we pick this constraint, and then we move on to the next constraint. We never go back. We never revisit the same function or same piece of information again. Okay, all right. This is our constraint. Now, for the case of phase retrieval, the form of the function f is this. We don't need to worry about exact formula here. What we need to understand is that what is going on. You can think about the dynamics of the algorithm as at any given iteration being represented by the current estimate x, which is a point in n-dimensional space. And the next time you have some update based on some random measurement, so it's going to be a Markov process in Rn. Okay, that's the fundamental way of understanding this kind of iterative algorithm. All right. Now, how do we measure the performance? The performance is measured in terms of the square distance between my current estimate and the true signal. But because we're missing the sign information, there's a fundamental ambiguity. X star can be the true solution, but negative X star can also be the true solution. So let's just say take the minimum of these two possible points, and we get this performance metric. It's a summation of three terms. The first term is the norm square of the true signal, which is fixed. The second term is the norm squared of the current estimation vector, okay, the length of the current vector. The third term is the inner product between my current estimate and the true signal. Or geometrically, what we care about is at any given point, how long is this vector and what is the angle made between this vector and the true signal, right? These are the quantity that we care about. Although this point, x of k, is going through a random walk, a Markov process in Rn, okay? Now, what we do is we define the length as bk and the inner product as ck. These are the two scalars that I really care about. I don't really need to know the details of n-dimensional space. I only need to know these two quantities, okay? So let's write out the dynamics of these two quantities. And the dynamic of these two quantities can be written out in this form. It involves two random variables u and v that are equal to a random projection of x star and x of k onto a Gaussian vector, okay? So here it is one very important property of Gaussian vectors that we use. It is rotationally symmetric. That means it doesn't really matter how these things are rotated, as long as they are relative position, the angles, and the length are kept fixed, then every time you are seeing the same Gaussian. Okay, that's just a high-level explanation of what is going on. And because of this, we can show that originally we have an n-dimensional Markov process. But if you only focus on these two variables, these themselves also form a Markov process. Okay, so that means I only need to study bk and ck. I don't need to worry about n-dimensional space. That's not obvious because bk and ck are functions of this n-dimensional vector. So their dynamics should be a hidden Markov process. But here what we are proving is that they form a Markov process. Okay, so here is just some simulations of b, the length, and ck. If you start an algorithm somewhere and you let it run, and after a while it will converge to these two solutions. Okay, so that's sort of nice because we don't need to worry about n. N can be very large. Irrespective of n, we only need to worry about a two-dimensional Markov process. But what is not nice yet is that this algorithm or this process is a Markov process or Markov chain defined on an uncountable state space. Okay, B and C can be really any point on this space. It's not easy to study or understand or analyze this process. But fortunately, we can see in this formula, the update formula, the update step from bk to bk plus 1 is order 1 over n, where n is a signal dimension. So if n is very large, then although this is a random process, it's a Markov chain, it will no longer have any randomness left. Okay? The trajectories will converge to solutions of deterministic ODEs. Okay? That's in the large n limit. This is what is going on. And then you can show that, but of course, the trick of doing time rescaling, you have to scale the time correctly. But after doing that, we can say that there is a continuous function, bt, and the continuous function, ct, which is angle. And you have two nonlinear ODEs. And these two ODEs, which can be computed from the actual dynamics of this process. And what we claim is that these two ODEs are going to tell us exactly the performance of this algorithm when n is large enough. Okay, that's what we get. Now, I don't just say go through the proof, but let's see some numerical simulations. Here, this is a rescale time in this algorithm, and the black lines are the solutions of these ODEs, and these dots are Monte Carlo simulations of this randomized algorithm. You can see this ODE predicts the performance very well, and I don't think you will be able to see it from behind. There are actually error bars, okay, 2 standard deviation error bars. The size of error bars are even smaller than the size of dots. So it's highly concentrated for n equal to 2,000, which is still reasonable. It's not like 2 billion. So n 2,000, it's already getting some nice concentration behavior. And from these two quantities, we can compute MSE. This is the MSE, again, predicted by theory versus what is actual performance. So from this figure, we can also see that this, the usefulness of this ODE approach is that the MSE does not have monotonic decay, right? There's initial phase of increasing MSE, and then you have decrease. Okay, so if you use standard approach to analyze the convergence of this algorithm, it tends to be more challenging because you need to take into account there is an initial increase phase. But ODE exactly tells you what is going on, and this is some very powerful tool. Okay. All right. So I sort of omitted one important detail. Okay. For this entire ODE limit to work, there is a condition that I didn't cover. The condition is that you have to start your algorithm correctly. Okay. What is the starting point? Here, C is nothing but the angle or the inner product between your true signal and your initial point. We're saying that they cannot be equal to 0, meaning the two vectors cannot be orthogonal. If they are orthogonal, the inner product is 0. We're saying as long as you start at a point that is not orthogonal, then you are going to be fine. You will converge to this ODE limit. Okay. Okay, then you say, how hard can this be, right? So suppose you have x of star, which is a point here, okay? And you randomly draw a point, a vector. You take the inner product, okay? I want to make sure that the angle is not 90 degrees. It's as long as it's less than 89 degrees, I'm fine. And it looks like it's very likely. Just randomly draw a few, and you're going to have a nice initialization point. But the problem is in the high dimensional limit. In the large n limit, it's actually extremely rare or difficult to have a randomly drawn point to be not orthogonal to the original vector. Okay, it's a peculiar nature of high-dimensional sphere. So if you randomly draw a Gaussian vector, chances are that you are getting orthogonal. Okay, you are being orthogonal to the original vector. So it's a very challenging problem to get a correct initialization. So for initialization, we use this beautiful algorithm proposed by Netropoli and so on. So it's a spectral algorithm. It's a very, very simple algorithm. What you do is let's build a matrix A, which is a linear combination of AM, the acquisition vector, and its transpose, weighted by the measurement, YM. Okay? You build this. And then you get an n by n matrix. Once you have that, you compute its leading eigenvector. The claim is that the leading eigenvector is going to be aligned with the true signal, okay? Which, as I said, is very rare if you randomly draw. It's not going to be aligned. So this algorithm clearly is working. So why does it work? There's a hand-wavy explanation. The hand-wavy explanation is the following. If you look at A is a average or empirical average of a large number of independent entries. Okay, when M is large, this empirical average is going to converge to the expectation, which can be computed. If you compute the expectation, you will see that the expectation, which is a matrix, is identity plus a rank 1 update, where the rank 1 space is exactly pointing towards the correct signal. Okay, that means if this is indeed equality, then the leading eigenvector is going to be exactly equal to the true signal. But of course, this is not equality because the matrix is also growing. It's not standard convergence. Okay, but still, this is the leading eigenvector is going to give you some useful information. And in our work, what we first characterized is a lower and upper bound. We're saying that if you do this experiment, where the horizontal axis is m over n, the number of measurements divided by the number of dimensions. Okay, alpha has to be large. You are oversampling the system, and in the large n limit, we're saying the angle or the cosine of the angle, which is the number between 0 and 1, must be lower bounded by this red curve and upper bounded by this blue curve. There are closed-form formulas for these curves, and there are multiple phase transition points. In particular, we're saying that there's a critical alpha. Okay? If your oversampling ratio is above that, you can guarantee the largest eigenvector is correlated with your true signal. Okay, it's a non-zero. So, and then I don't think I will go to the details of this. Then we also did the replica calculation. I didn't explain what the replica calculation is. Is a very powerful method from statistical physics that allow us to compute quantities like this in the large n limit involving randomness. We can compute the concentration value, meaning that in the large n limit, the inner product will be concentrated around certain values. So here, this is a simulation. The green lines are the actual realization of the inner product. Okay, and these dots are the empirical average, and the blue line is what is predicted by the replica method. Okay, so there is clearly there's a phase transition point, and the red line and the yellow lines are the lower and upper bound. Okay, so so that means, according to the replica prediction, your oversampling ratio must be greater than this point. Then you're going to have a nice initialization. You're going to be correlated, right? Okay, right. But if you want to be sure, then you go to the lower bound, right? Okay, just as a summary of this talk, we considered row action methods. I think by now you should know what I mean by row action methods, right? So because in the case of a linear projection, every time I pick a row, I do projection, and it cannot be extended to the nonlinear case. So for the just say nonlinear, for the linear case, we use lifting to compute exact MSE. For the nonlinear case, we use the rotational symmetry of the Gaussian ensemble to reduce the dimensionality. And also in the large n limit, the dynamics are governed actually by deterministic ODEs, which are easier to analyze. Okay, and then we know we can study the convergence behavior. Okay, suppose you have a tolerance of epsilon, then how many iterations you need to run? What is the current MSE? We know everything by studying the MSE. And also the last step, we also studied the spectral initialization.
Welcome to Unified Conferencing.
Yes.
You are the first person to join the conference.
No, we're done. I mean, so and then we get lower bound and upper bound. Also, we get some theoretical predictions given by this replica method. Okay. All right. I think I'm done. Thank you for your attention.
We have time for a couple of questions. Yes.
So about the dynamics part,
Yes.
You were showing that the update equation is governed by a product of this Q1, Q2, Q3, the random matrices, right?
Yes.
So that's more like a switching system because you're switching from one matrix to another matrix for
Yeah.
iteration.
Sure.
So So in control theory, we make a distinction between switching and time varying, essentially. So say, for example, if each of these matrices themselves were explicit functions of K, each of these matrices are constant matrices, right? They vary with iterations, but they themselves are constants.
So you have a fixed ensemble of these. Suppose you have a bag of matrices. Every time you pick one randomly,
Right,
and next time you pick another one.
Are constant
They are not time varying.
Right.
I mean, just the bag is not time varying. But every time you pick one, I mean, different realization can pick different ones.
So say for example, if these matrices were indeed functions of K, then what would happen?
So you mean every time you have a different bag,
Kind of, yes.
it will work. Essentially, then what I think I just say, then what will happen is in the formula. In the formula, what we have here, we say it's this matrix raised to the power of n. Okay. Now, if you have time varying, then it's nothing but the product of an average over this this ensemble at every given iteration. Okay. It's the same issue. Yes.
Any other questions? Okay, so I'm kind of wondering, your analysis was in a noiseless case. Can you say anything when there's measurement noise?
Which setting? This one, linear.
Yes.
Yes. In the noise, there are multiple. Just say there are multiple ways of studying this. One is you still use this noiseless algorithm, but you apply it to a noisy case, right? That's one. And then what you can do is you will show they will not converge to zero. They will converge. MSC will converge to an error floor. There is I think this is what we showed actually in this case. There is an error floor, right? It's not zero. This is 10 to the -2. There's an error floor. Now, there are variants, right? Because if you know there's noise, it doesn't make sense to use an algorithm derived based on noiseless assumption. So there are variants about, just say, approaching the least square solution, the pseudo-inverse solution. It's actually the same math. It's a little bit more complicated, but it's actually the random linear recursion scheme, and this can be used to analyze it. It's actually the same thing. Yes.
I have a question about the last part of your talk. In this, I'm not
Yes.
up on the literature on basic retrieval.
Mhm.
I did see contests
Yes. Yes.
on this problem.
Mhm.
But my understanding, walking away from the talk, that he was actually reformulated the problem as a convex problem, and
Yeah.
and showed that he could
Yeah.
actually
Yes.
he could
So
get, beautiful results.
yes. So here, indeed, the for a while, the state of the art for phase retrieval is indeed this convex relaxation, because knowing the absolute value is equivalent to knowing the squared, right? The inner product squared. That's equivalent in a noise-free case. And then you say this quantity is actually equal to a linear measurement of a matrix. It's the inner product of a matrix, and it's a linear measurement matrix. But with the knowledge that this matrix is a rank 1 matrix constructed by X star and its transpose. Okay, and then the problem becomes recovering a matrix from its linear measurement. But you don't have enough measurement, so you cannot just do simple linear recursion. You have to use the fact that it's a rank 1, which is non-convex. And then they say, let's relax the rank 1 constraint by minimize so-called nuclear norm. That's the, and then this is the convex relaxation, yes, scheme. And the solution is based on semi-definite programming, yes.
But you said also that basically, practically, it was difficult to.
It's yeah.
I guess
Yes,
I
it's
see
practically
I
yes.
see a disconnect here, because he claims that he solved the problem,
Yes.
and you're saying that
Yes.
practically it's actually no solution.
I mean, in theory, this is just a convex problem. Okay, so in theory, it's solved, but it's just that the computational complexity. I think for people working on semi-definite programming, they say hundreds are the limit.
I see.
Yeah, if you see, even for simulation, I mean, they cannot go to thousands. Okay, they have to do something more. just say directly solving as semi-definite programming.
It's a limited solution.
It's just say in theory you can prove everything, but actually when you, in practically speaking, and the algorithm that we presented, the total cost is order n to the power of 2 versus n to the power of p, where p greater than or equal to 3. So there is a factor of n improvement, and n can be the signal dimension, which is can be very large. That's just say the benefit of going to non-convex alternative. You never really work with matrices. You work with vectors. Okay, but the challenge is, of course, you want to prove, because you can say any problem I can run gradient descent, but is it possible to prove that although you are dealing with a non-convex problem, you can still converge to the true solution? This is what we did. I mean, but with proper initialization. And so
practically for like let's say a moderate-sized problem.
yes.
What are we talking about in terms of time?
So I think for each iteration, it's extremely efficient. For n, I think for trying n equal to 2,000 is like real time. Just say running, for example, 100 iterations. It's very, very fast in the range of maybe seconds. Yes.